Manage to relate to the student. This is like
Okay, guys, this is a part two. Okay, this is a second part for the video on drawing Lewis structure. So it is important that you watch this part two so you can know exactly the extension to the octet rules. The objectives for this lesson, we will be able to distinguish between a covalent bond and a coordinate covalent bond. We will also describe how the strength of a covalent bond is related to its bond dissociation. We will identify exceptions to the octet rule. Very important. What are coordinate covalent bonds? Coordinate covalent bonds. A covalent bonds in which one atom contributes both bonding electrons. They are sharing, but that pair of shared electrons comes only from one of the atom. For example, when you draw the Lewis structure for carbon monoxide, carbon has 4 valence electrons, oxygen has 6 valence electrons, and this is the Lewis structure for carbon monoxide. And which one is contributing to those shared electrons? This is the orbital notation. Carbon 1s2, 2s2, 2p2. Oxygen 1s2, 2s2, 2p4. And they are sharing 2 pairs of electrons. This is what happened. Oxygen has 6 valence electrons. Carbon, so they are sharing a pair. But carbon has 4. Carbon only is sharing the other pair of electrons. Coordinate covalent bond, a pair of shared electrons, that is, they are sharing that pair, but that pair is coming from only one atom. Not both of them are not contributing to that pair of shared electrons. What is bond dissociation energy? Is the energy required to break the bond between two covalently bonded atoms. Okay, the stronger is the bond, the more energy you need to break it. A single bond is weaker than a double bond. A double bond is weaker than a triple bond. So a single bond is weaker than a triple bond, but a single bond is longer than a double bond. A double bond is longer than a triple bond. Okay, the shorter it is, the stronger. Just imagine a stack of a stick. You have only one stick, it is long, it's easy to break. You have 2 sticks put together, it is stronger. You have 3 of them put together, they are even stronger. Now, there's another term that is not in the chapter I need for you to know. It is the lattice energy. When you have a crystal, you have an ionic compound, okay, that form a lattice structure. So the lattice energy is the energy needed to, you add energy to break bonds. Adding energy to break bond. That's mean breaking bond is endothermic. Forming a bond is exothermic. I'm going to repeat this. It is on your unit test. To form a bond, energy is released. To break a bond, you need to add energy. Lattice energy is the energy released. That's mean it is negative. Released to form 1 mole of an ionic compound from its gaseous ion. If I start, so this is the opposite I put here. If I start with the ions, I start with potassium ion, it's a gaseous state. I start with chloride ion, it is gaseous state. I put those two ions together to form 1 mole of potassium chloride in a solid state as a crystal. The energy that is released to form that ionic compound, we call it a lattice energy. Lattice energy is always negative. Lattice energy always negative. In some books, you can say it as the opposite. It says it is the energy associated with separating 1 mole of an ionic solid into its gaseous ion. So this would be positive because you are breaking the bond, you add heat. Let me repeat. Lattice energy is negative. That means energy is released to form 1 mole of an ionic compound from its gaseous ions. Okay, what is the Coulomb law? Coulomb law used to calculate the energy of an ionic compound. So you have energy equally constant. Don't worry about this. We don't use it in chemistry. It is a constant time, the charge, the product of the charges of those two ions over the distance between them. If they have a higher charge, those ions have a higher charge, they have a stronger energy, stronger Coulomb force. It is stronger lattice energy. You need more force. Okay, so over the distance between them, the larger is the ion, the larger is the distance between those two ions, the weaker will be that bond. They are not held tightly together. Okay, so now this is the part where you need to pay very, very close attention. Let me see if I can do that so the video won't be too long. So help me. Periodic table. Jordan-Lewis structure 4. Beryllium fluoride. Beryllium is in group 2. It has 2 valence electrons. Plus, fluorine in group 7 has 7 valence electrons. Time 2 give me 14. I have a total of 16 electrons to place. My central atom is beryllium because the least electronegative. And whenever you have only one atom and 2 or more of the other one, that one will be central. So I have beryllium and I have 2 fluorine. I just put them as far from each other as possible. I connect them by a single bond only. I should always start with single bonds. So I have used a pair of electrons here, which is 2, a pair of electrons here. It is 2. 2 plus 2 give me 4. 16 minus 4 give me 12. So I have 12 electrons to place. So I have 2 here, 4, 6, 8, 10, 12. I already placed everything that I had. Fluorine is stable with 8, but look at beryllium. Beryllium has only 4 electrons around it. Write this down. Beryllium is stable with only 4. That's okay. It is an exception. Beryllium does not need to have an octet to be stable. So, on your note, for the exceptions to the octet rule, I need for you to write down hydrogen. Hydrogen is always stable with just 2 electrons. Hydrogen stable with 2. Should never try to put more than 2 on hydrogen. Now we have a second case here. Beryllium is stable with 4. Don't try to force to put more on it. It is okay. It is stable. Now let's continue. We have, I will keep erasing, so make sure you stay with me. This is boron. Boron is in group 3A. It has 3 valence electrons. Change back to blue here. This is 3 valence electron. Fluorine has 7. 7 times 3 give me 21. Equal 24. So this is only 1 boron, 3 fluorine. Boron has to be central. And I put my fluorine as far from each other as possible. So I already used 1 pair. 2, 3 pairs give me 6 electrons. 24 minus 6 give me 18. I have 18 to place. I'm going to be lazy and put a dash here instead of 2 dots. Sometimes you will see it like that. It's not that bad. It's okay. Alright? So this is, I have 18. 2, 4, 6, 8, 10, 12. 14, 16, 18. Okay, fluorine is stable with 8. Fluorine has 8. Fluorine has 8. I already used everything that I had, and I need for you to look at boron. Boron has only 6. Write down that boron is stable with 6. It is okay. Hydrogen 2, beryllium 4, boron 6. Alright? Now, let's reset and continue. This is phosphorus tetrachloride. Okay, let me go fast. I have pentachloride. Thank you. Pentachloride. So, phosphorus is in group 5A. So, it has 5 valence electrons. This is 5 plus chlorine in group 7A, 7. 7 times 5 give me 35. 35 plus 5 give me 40. Phosphorus has to be central. It is less electronegative, and you have one, just one of it. So I'm going to put phosphorus right here. I have 5 chlorine. This is 1. It is chlorine. 1, 2, 3, 4, 5. I put them as far from each other as possible. Just pretend they are as far from each other as possible. Okay, 5 of them. And the 5 bonds. 5 times 2 give me, I already use 10. Okay, keep an eye on me. If I make a mistake, you stop me. This is 30. I have left 30. So let's go by 2. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. I use everything. Let me show you that each chlorine has 8. Each chlorine has 8. I need for you to look at phosphorus right here. Phosphorus has 10. Here's the rule. Here's the rule. There are so many of them, I don't even call them exceptions. I'm calling it a rule. Listen carefully and take notes. I did not write it down for you. Any non-metal from the P blocks starting with period 3. Period 3 going down. When I say down, I mean on the periodic table. That's mean period 3, period 4, period 5, period 6, period 7. Going down on the periodic table. Those elements can have an expansion of the octet. That's mean they can hold 10, they can hold 12 electrons on the central atom. Okay, I will repeat. Any non-metal from the P block starting with period 3 going down on the periodic table, that's mean period 3, 4, 5, 6, 7, can have an expansion of the octet. That's mean they can hold more than 8 electrons. Alright? So, nitrogen cannot. Okay, because I said period 3 down. Why can they hold them? That's because we have the d orbitals available to put electrons. Even when the d is empty, you don't have anything on it when you draw the Lewis structure, but from period 3 down, the d's are still there. You can put electrons on the d. Alright, let's reset and move on. This is SF6. S, group 6, 6 valence electrons. Plus fluorine 7. 7 times 6 give you 42. 42 plus 6 give you 48. So I really have to go fast. This is my S, and then I need 6 fluorine. 1, 2, 3, 4, 5, 6. Okay, now I'm going to put my pair of unshared electrons. I'm going to put them as dash. But remember, you have more time. You can use that if you want. And since I want to go fast, let me count in French so I can go faster. Okay, let's go. I have used 2, 4, 6, 8, 10, 12. Already 12. Minus 12. Give me 36. I have 36 left. Let's see how fast can we go. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. So I use 36. Okay, all of them. And each chlorine is stable with 8. But each fluorine stable with 8, no problem with that. Look at our sulfur. Sulfur has 2, 4, 6, 8, 10, 12 electrons. It is okay. Non-metal from the P block from period 3. It is okay. Alright? Don't cry over it. It is okay. Let's move on. The time is running and I have to finish with the exceptions. We don't want a part C. I need for to look at NO2. Another exception, NO2. This is N is in group 5A. It has 5 valence electrons. Plus oxygen group 6 has 6 plus 2 give me 12. The total is 17. Okay, central atom is nitrogen. I have 2 oxygen. Put them as far from each other as possible. And I already used 4. 17 minus 4 give me 13. I have 13 to place. Okay, 2, 4, 6, 8, 10, 12. I have 1 left. This is 13. I use everything I had. This is very strange. So, what do? When I don't have enough, I use everything I had. I don't have enough. What should I do? I replace a pair of unshared with a pair of shared. So I share this one with nitrogen. Okay? Each oxygen is stable. Oxygen stable. Nitrogen has 2, 4, 6, 7. I cannot share a pair again because it will go over 8. It will be 9. And nitrogen is in period 2. Nitrogen cannot hold on expansion of the octet. Nitrogen has 7. Here's the other rule. When the total number of valence electrons is odd, when the total number of valence electrons is odd, you need to give the central atom as many as possible to get close to the octet, but it will not have that octet because it is odd. Alright, so we try to give nitrogen as close to 8 as possible. If the total is odd, so the central atom will be an exception. Now, we could even draw a resonance with this. You can flip that double bond here and put a single bond here. Resonance. Because of time, I'm not going to do that. So I need for you to make sure you know the extension to the octet rule. I will stop here and then another video is on the way. Enjoy the rest of your day. Bye.